Hello, everyone. Thanks for coming. I'll be presenting today putting TensorFlow 2 models into production. TensorFlow team released this year TensorFlow 2 into production. It is no longer alpha, it is no longer beta, it is no longer release candidate, it is production ready. And today I will be mainly talking about TensorFlow 2 updates that happened on the TensorFlow 1 and how do we deploy these models into the production. I was searching an image on how to deploy TensorFlow models into production. I find this image very absurd, where it basically suggests that you have a phone, you click on a TensorFlow logo, and then it just deploys the model to the production. I wish most of the things are that easy. Maybe this will take another 10, 15 years to go from what we have right now to deploying the TensorFlow logo and then deploys this into the production. A little bit about me. I work at Walmart. I have been working in Walmart for about a little bit more than 3 years now. I was part of the Jet.com. I used to do recommendations and query suggestions there. My team then, after the acquisition of Jet.com to Walmart, my team did visual search for HeyNeedle. HeyNeedle is another company that is part of Walmart that does home and furniture products. And then now we are more and more focusing on the textual search in Walmart.com as well as store search. We are hiring this year pretty aggressively. We are going to hire 10, 15 more software engineers or machine learning engineers. If you are interested in an open position, either in Sunnyvale, San Francisco, or Hoboken, New Jersey office, please shoot me an email. And I will be sharing the presentation as well as the notebooks that I will be going through in my Twitter account there. Before the talk, I kind of want to set the expectations where I won't be talking a lot about building models. I won't be talking a lot about training models. I won't be talking about a lot of data processing and validation. The idea is not so much about me talking about these concepts, but rather I want to spend a little bit more time on what goes after you train the model, what goes into after you build the model. I will be showing the building piece as well as the training piece, some of the examples for TensorFlow datasets. However, most of my time is going to spend on what goes next after you have the model, after you train the model. The training model is already a solved problem anyways, so why do you even kind of talk about, right? You have this machine learning system. It is a pile of linear algebra. You put some data. If it doesn't work, you put more data and stir the pile and then try to see if the results look good. So the talk has the TensorFlow name itself, and this talk is mainly about TensorFlow. And TensorFlow has a number of advantages over other libraries. Google defines end-to-end open source platform for machine learning. This is more like an aspirational description than it actually what it is. It is not really a platform. It is a machine learning library, and the key piece of it is actually it tries to be the end-to-end machine learning platform. Most of the libraries that you have out there is focusing on either the training piece of it or the building part of the machine learning life cycle, where they don't necessarily focus on the model deployment, how the model is drifting in production, what is the prediction latency, and a bunch of other stuff that actually makes a model to provide customer value in a real production setting. And this might be fine for the scenarios where you have a CSV file, where you have a database, and then you run an offline analysis, and then produce predictions, and then you output those predictions into yet another CSV or a SQL table. This workflow might be perfectly fine. In search, we cannot really afford this because the customer is very contextual, and all of the queries are in real time, and we need to serve real customer requests in a production, in a real time scenario. And TensorFlow is great for this type of production settings because it supports a number of things out of the box. I will spend a little bit of time for each sections in here. Not everything is as important as some of the other things, but overall it kind of provides all of the advantages of that library over all of the other available alternatives out there. The first one is lazy evaluation. Right now they also support eager execution with the TensorFlow too. Lazy evaluation provides you a way to define your computation beforehand, and then TensorFlow will understand what that execution, full execution entails. What does that mean is you now specify a number of operations that you want to operate on top of the data. And then when TensorFlow builds the graph end to end, then it can execute and it can optimize that graph quite a bit. While you may want to get benefit from that lazy evaluation aspect. The second, we are going to talk TensorFlow model serving quite a bit. They actually have a separate component that is fully production ready to make the serving layer of the model much easier. Most of the machine learning libraries don't provide this type of mechanism to make the model deployment easy. Available production-ready models, since Google supports, obviously, wants this community to be adopted because of research reasons, but also because I think their GCP strategy, they are also making a number of models available for anyone to download, anyone to use in a commercial setting, in a non-commercial setting. It has a number of models that are really, really performing well. It has also a lot of community support. The TensorFlow itself was released in November 2019, so 2015, sorry. It has been more than 4 years, and I think it is one of the mostly wide adopted deep learning library, comparing to, for example, PyTorch, which is much newer. It is open source. I'm not going to spend any time on this. This conference puts a ton of emphasis on the open source already. TensorPort is another excellent component that it provides out of the box, where you can do all of your analysis in a much better integrated environment with the TensorFlow. It also supports distributed training support. So if you are kind of provisioning a number of machines in GCP, then you will be able to use these distributed machines with fully natively supported from TensorFlow. If you have the GPUs in those machines, it can also utilize this GPUs. Currently, they also support TPUs, tensor processing units, which is available in Google Cloud Platform GCP to make the computation in a shorter time frame. Although the GPU and TPU machines are obviously much more expensive than the CPUs. As I mentioned, it is pretty widely adopted, and the adoption piece itself is not very important, but if you are facing a question, if you are facing a problem, when you basically get that error message and then type in Google, and then we'll be able to find the results or the solutions in Stack Overflow or in GitHub, that is very important for engineering productivity. So I mentioned all of the good stuff that it provides, but then why would anyone actually not use TensorFlow? The problem, it has also its own problems. Its debugging is not very easy. The stack trace as well as the internal error messaging are not very well implemented. Especially in TensorFlow 1, it needed a lot of boilerplate code to be able to just glue a number of pieces that are very important together. Interfaces are not very obvious to figure out. This always I compare with the scikit-learn. In scikit-learn, you don't need to know the class name. You know which function to call, which function to use, no matter what the model was, because all of the models share a very common interface. So you don't have to think a lot about what to call, even on the object level. Where in the TensorFlow, there are many ways to do things, and some of the interfaces are not very obvious to figure out. Some of them are using interesting names. Some of them are just not very well supported. This place also ended the second piece of it. It was very cluttered library in the TensorFlow 1. They created a new submodule, which was the contrib, and contrib actually get a lot more contribution from community. That was great, but then nobody really supported, maintained that piece, and then over time, the maintenance become really hard, and then people are using different types of submodules to do the same exact thing, and it became really hard to maintain. It also didn't have dynamic graph support in TensorFlow 1. Now they support dynamic graph support. And all of the errors, problems that I mentioned, that was actually specific to TensorFlow 1. It is now a bit better. For example, interfaces are so much better because they adapted most of the places Keras' interface. They deprecated, removed a number of modules in TensorFlow 2. Basically, they are basically saying that we are no longer supporting this. Boilerplate code is very minimal now. It is not in the same level as PyTorch. PyTorch, I think, is one of the best libraries that get actually right. No boilerplate code. You just write code that actually matters. However, TensorFlow is also going there. And they provided TensorFlow datasets. This is not so much about specific to TensorFlow 2. However, now it is much more maintainable and supported much more robustly by the TensorFlow team. And now TensorFlow Hub, which you can consider GitHub for the TensorFlow models, is natively integrated into TensorFlow 2, which I will explain what it means a little bit later. As I mentioned, the disadvantages are a little bit less now. Overall, if you look at kind of the TensorFlow 2 ecosystem, you can consider there are two main components, training and deployment. And then you have an interface between training and deployment for serialization, for model repository. On the deployment piece, it is basically producing these predictions to the customer. On the training piece, it is the most commonly understood data science flow where you have a number of data, and then you build your model, you execute, compute that model, and then through analysis, you iterate on top of this. When you think you have a good model, you kind of serialize that, and then after that, it is part of kind of the deployment piece. In Walmart, generally, this is done also as two separate teams. So it is very important to have a common interface where the engineering focused teams are more interested in this piece, and the data science teams can implement this piece. And in software engineering, right, if you kind of try to make a comparison, software engineering is very similar kind of CI/CD pipeline piece where you do your code changes in here. You write your unit test, regression test. After you get your PR reviewed, that creates an artifactory that gets pushed into an artifactory repo or some other mechanism. And then now the DevOps flow will start where you put your artifactory, and then now let's create a deployment strategy to be able to deploy that code change. Obviously, machine learning is not as mature as the software engineering. So they are, I think, trying to borrow some of these ideas to be able to implement. And especially the state model is making a lot of progress. And with the TensorFlow 2, now it is much more elevated, de facto serialization format for training as well as the deployment. And now we can actually use the same exact state model to be able to download TensorFlow Hub models, which basically works exactly how you train the model. So it is no longer any different. There is no any difference between you pull a model from TensorFlow Hub and then you train a model on your own machine, and then you want to deploy those two models. As long as the serialization format is state model, it works exactly the same way. And in order to kind of even improve the situation, if you want to reuse some of the TensorFlow Hub components, you can also deserialize into the state model. You can retrain the same model and then push to the customer on the deployment piece. So this works now very seamlessly on the state model piece, which we are going to talk a little bit more on the state model. And the other things is TPU is only available right now, as far as I know, in GCP. GPU is available in if you want to deploy AWS or Azure based on your cloud provider. That works the same way. I just had an experience on the NVIDIA side, but I believe all of the other graphic driver companies would also work the same way. And the model design now, it is cast estimator, so it is much better. And the TF data provides a way to basically get the data on your site in a much streamlined manner. So I mentioned TensorFlow Hub. I want to spend a little bit of time on the TensorFlow Hub piece. As I mentioned, Google provides a number of models that have been already trained, and they are making this available for the community to use. And through TF Hub now, you can basically call the same exact sequential API that you want to use on the Keras, and then you can get the same exact model that Google built for ImageNet, and then after that, you can use the same exact model the way you are using your local models through TF Hub. The interesting piece is in here, if you are using a full-blown model on the hub, which is a TensorFlow Hub, I will show the notebook. This is not as important right now, but you can actually get the serialized model into your local machine, and then basically wrap that saved model, and then make it ready for you to deploy to production. This is going to be somehow important on the retraining piece that I will be talking later. And the TF Hub itself is not as important, maybe, right, on the infrastructure part. But with the transfer learning, as well as kind of these sharing models, most of the model architectures are becoming somehow separated. You want to learn your embeddings, your representation problems in here, and then you want to build your application-specific logic at the end on the classification piece. What does that mean is, if you already have a model that actually trained for kind of vehicle classification, let's say, in here, and you want to extend that model so that you can classify traffic signs or anything that is related to the vehicles, then you can actually get this model, put all of the images that you want for the other types of data sets, and then you can retrain the model. You can improve the feature learning piece. You can get all of the embeddings. And then if you are separating the feature learning and classification, you can kind of consider these as two different problems. After you improve your embeddings, you can build another classifier that will do traffic signs, as well as all of the vehicles that you have right now. And or you can basically combine feature learning and classification, and then retrain your models based on your needs. The second piece that I will be talking about is TensorFlow model serving. I will be spending quite a bit on this TensorFlow model serving because it is very crucial to put this in a production setting for kind of Dockerized version of these services. It has mainly 4 different components. This graph is a little bit reads from right to left rather than left to right. The client is actually making the request. So I will start with the source. The source is actually the place where the model sits. Basically, the place that you store your model. This model could be a protobuf. This could be a saved model. This could be an HDF5 file. This could be anything that can be loaded into the memory. And this source is basically implements this file system, which is a pluggable implementation, to make this model available. The loader, which implements the TensorFlow servable, which if you are using saved model, this is already TensorFlow servable, is responsible for loading the model. It says loader, it just loads the model. However, at this point, loader doesn't actually serve the request at that point. It passes a message to the dynamic manager that I load this model, I have the memory for this new model, and I am asking you to serve the request into this new model. And the dynamic manager through the version policy also pluggable implementation. You can implement blue-green deployment strategy. You can implement 10%, 20%, 30% traffic request strategies to be able to serve requests from old model to new model. And the dynamic manager, based on the version policy, is responsible for basically elevating the new model into the service. And then servable handle will just communicate and get the predictions from the new model through dynamic manager, and then you will be able to deploy this model through this flow. So this is important, and it is more advantageous comparing to what you want to build in your Flask applications in two different scenarios. The first one is the version policy. Most of the time, version policy actually needs to be implemented on the infrastructure level, where in the TensorFlow model serving, you don't need to really do anything. It will automatically be taken care of you if you specify your version policy correctly. The second piece, the memory resource constraints and everything else is handled in the loader. So in the application, you actually don't need to specify if I don't have the memory enough, what I will be doing when there is a new model. Loader will basically look at the memory usage, resource usage, and then will decide whether it can actually promote that new model into the production, whether there is a new resource or there is not a resource that will be completely isolated to the loader. If there is not resources, it will fail. It will basically print out a message. If there is a resource, then it will be able to say, dynamic manager, there is an aspired version that I want to deploy to production. This removes a lot of kind of headache on very common tasks that you might otherwise invest a significant amount of your time to be able to implement and put into production for this. And another good thing is on top of this, these are all pluggable, so you can use any type of source that you want. Instead of file system, you can use a different servable if you want to. And then version policy, for certain models, you may want to use a different version policy. And for other models, you may want to use completely different version policy. And I couldn't make it bigger, sorry about this. My HTML skills are not great. The continuous training pipeline fits in this very, so go ahead.
So I wanted to go back to when you're deploying it and it says it's the container is not big enough. Mm-hmm. Does it give you like a verbose output, like your container's too small by this amount, or the model you're deploying is this size and this is the size available?
It will give you the memory issue. I don't know if it says this is the memory that you have. This is the memory that I require. It says that it failed due to memory resource constraint or the issue itself. However, you may make, I think, based on some numbers, you can also probably output those numbers as well.
Okay.
Yeah. However, I saw for the especially memory, it says basically I failed due to memory resource constraints. I don't have any memory, basically. Yep. And in here, on the continuous training pipeline, what you want to do is you have this data, you want to learn on that type of data, and then you want to deploy that model to the TensorFlow serving continuously. And TensorFlow serving will take everything take care of everything for you to be able to deploy this model on the layer. And then the clients, based on that version policy, will be able to get the predictions from the models seamlessly. This is kind of the aspired, continuous deployment for the machine learning, where you want to be able to deploy models and without disturbing anything on the client side. And from very outside, right, what does this look like is you have this model file, you have this model server, client asks what is in this image, and then model server will say it is Panda with 0.89 probability, very high level on how it can work. I provided kind of TensorFlow.
So does the client have to specify like the specific model?
No.
Or
That is up to you. So you can, so in the endpoint itself, not the signature, but the model name will be there. So the endpoint itself basically will say this is an image classifier, or this will be the model name that you want to specify in the training piece. That piece of information will be there. In the endpoint itself also, the 1, 2, 3 will be also there. So client can know those version numbers. Basically, I want to get predictions only from 1, only from 2, so that you can put the deployment piece on the client rather than server handling. And or you can put in a wrapper on top of that, and then whatever the aspired version is on the latest model, you can serve the predictions all the time from there, and then client doesn't need to know anything. It is very flexible in that sense. It will basically have the model name and the version number, and then based on that endpoint, you will be able to get any type of predictions that you want. And the links basically will give you the hub and model serving. Now I will, if there is any questions, I will answer those, and then I will show a number of notebooks on how you can actually do this from end to end on the server client. You will be able to see the endpoint there too. Are there any questions so far? Yep.
Can I just remind you just to repeat the question if people ask questions in here so we have it?
Okay.
Audio. Thank you so much.
Sure. Yeah. Yep.
So I'll follow up and say, let's say I have an animal classifier, and then once it like classifies as like, you know, I give it a picture of an animal, it says, okay, well this is kind of a canine, right? And I'm okay, what kind of canine is it? Is it a corgi, or is it a Rottweiler? But let's say from the requester side, I already know that it's a dog, and I just need to know what type of dog it is. Like, am I going to have to build multiple inputs or multiple like endpoints for the user to be able to do that?
So if the question is if there is any multiple models on the server side, how do I get multiple predictions per model? Is that correct? So if that would be the case, you can create an intermediate wrapper on top of those two models and then get the prediction in a single time. If you don't want to do that, on the client, you can ask the first model, and then you can ask in the second model, which is probably more granular model for the K9, and then you will be able to get a much sub-granular dog type there. So the TensorFlow we've already went through. This is basically that small kind of continuous training pipeline and the serving piece. In here, the model 2, model 1 can be done on the client side, where you can actually get predictions from model 2, model 1, or you can basically say, I don't want to know what the server side models have, and then I just want to get the request and then response, and then you will be able to get it. If you want to do other things, not just the model predictions, you can create a very lightweight API on top of the models and then provide the predictions there. Currently, TensorFlow serving supports multiple models. However, it doesn't support any type of orchestration on top of those two separate models. So if you want to get the predictions on different models, you need to call separately. And then the one thing I want to mention is it also supports gRPC. This is Google's remote procedure call. With the TensorFlow 2, it also supports completely HTTP JSON as well. So basically, you have two different options. If you want to make it really performant efficient, you can use gRPC plus protobuf. Or if you want to use HTTP, you can also do HTTP JSON combination as well. In the TensorFlow 1, they only supported gRPC, so you always needed to write a HTTP wrapper on top of it if you want to do HTTP communication. Now you don't need to do anything. You actually don't even need to write any Python code. It just supports HTTP out of the box, which I will show on the later. And then I have the first kind of REST API example. I will be going through the Docker file. So the TensorFlow model server doesn't work in Mac. They couldn't fix this even in the TensorFlow 2. It works in Linux very well. And today I will be going through these Docker files all the time. I want to just see a quick hands. How many people have used Docker, containerization, Kubernetes before? Is there anything? Okay. Some people have used. I will go a little bit quickly. The Docker is basically a containerization library, or I wouldn't say library, but containerization framework. Let me put it this way. It is a virtualization machine on top of the machine that you have. This is not great definition, but bear with me. You specify a base machine, Ubuntu 16, that you want to use that machine on your local Mac. And then based on that Ubuntu, you can basically install anything you want. And the reason why we are trying to do this is because we want to have a Linux machine that will basically emulate a Linux box on our local machine. And the important thing is this TensorFlow model server. Google makes this available on the Unix machines, and then you will be able to get all of the TensorFlow model serving when you register their URL. And then after that, you can basically install through apt-get, update, and TensorFlow model server. In here, the important thing is I will show what this script does is, but for the gRPC and HTTP REST API, we are exposing two different ports. If you are using gRPC only, you just need to expose a single port. If you want to use HTTP, you want to just expose another port. And what this fashion emanist, yep.
What's the advantage of using gRPC over?
So the RPC is much more efficient than HTTP for communication. Google has a number of kind of comparison between HTTP and RPC. It is just much more efficient. For specifically Python and the TensorFlow context, internally they use protobuf. Protobuf with the gRPC in both model definition as well as how they communicate between client and server fits very nicely on how you would be able to communicate on the gRPC piece. So they basically provide a number of interfaces for the gRPC that you can basically hard code on what the response would look like. And then based on that protobuf, if your client is Java, if your client is Swift, if your client is Android, you will be able to use the same exact protobuf definition, and then we'll be able to share that schema between client and server. Yep. Currently, though, they, I think, trying to get away from gRPC, especially for community to adopt, because everybody was building HTTP wrappers. On Jet, we used to build HTTP wrappers because our scheduler, which we used, Nomad, which is a HashiCorp product, didn't actually know how to register gRPC services. So we didn't have any choice except build HTTP services, because otherwise we won't be able to even talk across the network between different services. Yep. And the fashionminist file is nothing but a bash script, which basically calls TensorFlow model server. And in the Docker file, I exposed the REST API, which is what I'm going to use as well. And then in here, in your question, the model name, fashion model, is going to be the URL path. Basically, whatever you want to specify there, you can basically expose that in the endpoint URL, and then we'll be able to call that model URL in there. And then let's see how this actually works. If we go in here, I'm going to build the Docker file. I already built, so it will be quick, hopefully. The thing that I'm trying to do is basically this, moving models as well as the script into the Docker. And then the execution is going to happen in here. And then after that, I will be able to run this Python notebook. And the models as well as other things are specified in here. So when I run the TensorFlow model server while the Docker is building, you will specify basically the model name in here. In the same instance of the machine, under models, you will be able to have multiple models that will register. This is very important to decouple all of the model deployments. So you can consider you have a same instance, and you have multiple Docker files that will deploy your application, that will deploy your models. No matter what instance will get which model, since you have multiple Docker files with the different models name, and it will register the same exact URL, this provides a consistency across the board without us necessarily doing anything. And the port is also something we can control. So as long as you share the ports and other types of models in here, you will be able to get very consistent endpoints for a number of things. I just get this data set from I think, sorry. There is a fashion minced data set from, I think, Keras. And today, what I will be doing is in here, I will train a simple model. I will save this model in the saved model. I will show a couple of things on what saved model looks like. And then this outputs a lot of log lines. And then in here. So after you have the model, if you are using the new Keras API, this saved model storing is as simple as this. This was very complicated back in the TensorFlow 1 days. You specify the model. You specify an export path, which you are going to load the model from there. And then you will be able to save the TensorFlow model into that location. And then I will do that. And then if you want to look at what this model looks like, you can click on this there. I will be sharing this. And they also provide a saved model CLI tool to actually see what this model actually is. This is also very important if you want to look at what type of tensor you need to pass, kind of what is the method name that it is going to call, and everything else. This also has a number of things. And in here, previously, you need to actually specify signature definitions on the saved model itself. Since we are using the Keras model now in here, we no longer need to specify the signature definitions. This is automatically embedded into the model specifications. So you will be able to reuse whatever you want to specify on the training into the predictions without necessarily specifying anything on the serving layer. This is also very important. So consider this kind of scenario, right? You have 10 people in the data science that are training different types of models. As long as the signature definitions that they are putting into the training same across the board, you can actually do the same exact signature on the client, and then it will just work no matter how you are saving that model. Because now, go ahead.
It's not like simple Keras model, like something that uses like subclasses or something that requires you to import the classes to. How would you handle that?
If it is using still Keras's, even if the model is very complicated, you will be able to use this. If you are not using the Keras's API, then you still need to specify the signature definition in the old way. basically in the, have you ever used TensorFlow 1? In the TensorFlow 1, you basically need to specify input definition, output definition. You still need to do those. Yeah. If you are using the Keras API, you don't need to do you don't need to do those anymore. Yep. And the fashion minutes file is, if you are familiar with this minutes dataset, it is very simple, like 0, 1 up to digit 9. This is basically trying to emulate that dataset, except in a fashion setting. The images are very similar. It is, 28 by 28, and then it has 10 classes, it has dresses, it has a bunch of other things. And then if our Docker is built, now I'm going to just run by exposing the 8101 to here, and then it will basically show. So let me make it a bit bigger, actually. Maybe I'll just delete this piece and make this very tiny. So in here, I kind of like this a bit. It basically gives all of the log lines to you on what it actually is doing. You have this X model, you have this RCNN model, you have this other model. Actually, I think I did build the wrong model, for example. This is not correct because I was looking at the mince model. Sorry. This is correct one.
Did you post the lab notebook anywhere?
I did actually. Let me. Do you want to do this? Maybe I can write it down in here too. I think this should go to a GitHub repo. If it doesn't, let me know.
Yeah, I got it.
Yep. Yep. You can follow on. Sorry. I think the one or two may not be there, but most of them, the first 3 should be there. The first, maybe 4, yeah. I will update by the end of today. Yep. And, okay, this is perfect. And now I have the build. And I will do... Perfect. So in here, as I was mentioning, this is great. It actually is telling us what it is doing. It's basically looking at adding fashion model version 1. This is important when it tries to update a new model on top of here. The servable version is also basically showing all of the earlier examples that I was giving. And the reading saved model from the app models 1, this is basically the local that I am storing, where I am storing the model itself. And it shows a number of things related to the TensorFlow binary, how it is not optimized for the TensorFlow, which is not a concern for us, but for production deployments, you may want to look at it. You can also provide warm-up files. So if you want to basically make sure that the model is warmed up before, you can also provide warm-up data files. Unfortunately, I don't have this example in my notebooks today, but you can also do that. And then the most important thing is it registers for the gRPC on the 8500, which is what we specified on the Docker file. And then on the REST API, it is 8501. which is the HTTP REST API endpoint, which we are going to use notebook. And you can now consider, right, the terminal itself is going to be this my server. I built my model. I built my Docker file. I'm now running my Docker file in an instance. AWS, Azure, GCP, doesn't matter. I now deployed my model. Now I'm going to get predictions over HTTP. And then if I want to look at the status response, right? This is also another important thing. If you want to create a kind of health check, heartbeat type of mechanism on your service, we haven't written a single piece of Python code right now, right? We had a single model. We wrote a single Docker file, and it automatically exposes a status URL for us to consume to get the health checks as well as heartbeat to make sure that this model is actually up and running. If you look at the metadata response, now this is your question, where if you need to actually specify the signature definition on the model's saving. We haven't specified anything on the training piece because the Keras API took care of that for us. However, if you are not using the TensorFlow, you still need to define the signature definition because TensorFlow model serving under the hood is going to look at that signature definition on to see how to get that prediction. So that contract between TensorFlow model serving with the external still needs to be there. And in here, if you look at, this is very similar that inputs, outputs that we used to use in TensorFlow 1, and the method name is also similar on the metadata piece. And then the JSON response, you can basically look at the prediction URL. And the prediction URL is nothing but the predict method on top of the model itself. And then in here, you can look at predictions piece. Basically, it will return all of the probabilities. And then if you look at the class name, which is the predict, maybe I can use actually this. This will be my prediction from the model that I will be getting. And in here, basically says the model was thinking it was an ankle boot, and it was actually ankle boot on the training piece. And if you want to show these multiple, you can also similarly do this on the data set. This is a somehow relatively simple data set. I think the model has like around 90% of accuracy. So it is hard to find somehow the misclassification piece, but it is possible. So this is the first example. I kind of showed, if you have if you don't have anything, how do you kind of build a model through Keras's sequential API and then basically train this model. The second example is also very similar, except we are going to do a little bit differently, where we are going to submit an image on top of the local. Let me build that Docker file as well while we are going to go through the I can do this, I think. So this is somehow related, except I'm now putting some of my function on how we are going to put these images into the notebook itself. So in here, server is still going to be terminal. Server is still going to be the Docker file that I'm going to build, and I will be running. However, I will be passing an image, and I will be encoding that image into a prediction request, base64 encoded string, and then I will be posting that request, and then we'll be getting the predictions from there. And then I will be doing some sort of average latency to see how fast the model is. The average latency is not going to be anything meaningful because it is local. There is no network communication. There is no anything. But even for the sophisticated models that doesn't have a lot of different layers, the performance is actually pretty good. Comparing to if you load the model into memory and not run through TensorFlow model server and then get the predictions. So you can do this based on the Keras API itself. It is actually taking longer time than this, while this actually needs to create a separate port within your local machine and then get the predictions, which kind of stresses how good the TensorFlow model server is in order to get the predictions, because you cannot get the similar performance when you load this model into the memory and then use the Keras function on top of the model file. This will be very similar to the earlier example, so I won't be spending a lot of time there. I will just execute the same way. I'm still exposing the 8501 because, again, I'm going to just use, I need to kill the other word because I can't use the same port. And now, in here, I should be able to get the models. Baybars is a library that we open sourced in Jet. It has a number of util files, but it is not very complicated library if you are wondering what it is. And then if you look at this latency, this is generally around 50-60 milliseconds, which is really good for this type of data set. And then if you want to get predictions, sorry, there is I think a bug. Yeah, you can get the output predictions from the server side. This is a cat actually, but I think the classes themselves is kind of cat related, except it is not really kind of like cat family, I guess. This will be my second notebook. The third notebook I want to go is this notebook. Image mobile net. Yep. Perfect. So this example, I mentioned TensorFlow Hub. And in here, I will be using a TensorFlow Hub model. And then basically go through the same exact process that we went through, just to showcase that we can actually reuse some of the TensorFlow Hub pieces as well. And if you kind of look at in here, you basically need to specify a TensorFlow Hub URL. And based on the TensorFlow Hub URL, this is just a data piece. You will be able to load that into the model, and I will show how we can do that actually. Yeah, this is a module handle, and then through that you can get this piece. So this is what I was showing in the previous slides. I am just using Hub Keras layer because under the hood, all of the, I wouldn't say all of them, but some of the models provide this type of layer approach where you can actually get multiple layers from another model, and then you can build on top of yet another model. In here, you can basically get the module handle with the trainable false, where we are not going to retrain in this notebook the original model, and then you put on top of another layer, and then you can build the model, or you can basically keep using the same exact model with a different layer structure, and then build on top of that. In here, basically, we are getting the original model from TensorFlow Hub, and then we are going to specify this on the model itself, and then we'll be going through the same training piece to show, and then I will be saving the model and then showing this. This will take quite a bit of time, so I won't go there, but the thing that I was mentioning, since now all of the TensorFlow Hub models also implements the saved model. When you save the model, this is nothing but again saved model that you can just deploy wherever you want. This is pretty powerful because now I pulled some other model from another repo on the TensorFlow Hub. I now know what is the signature definition, what is everything else, and I know the model name. I know basically everything about the model. And then I save the model into my local machine. Now this model can be reused for my own purposes, basically. This is pretty powerful for reusability purposes. If you know the layers as well as other things, you will be able to reuse some of the models in a better environment than what we used to do in TensorFlow 1. In TensorFlow 1, this wasn't this easy, this piece, because the TensorFlow Hub didn't implement the saved model as their de facto serialization library. So that the TensorFlow Hub didn't actually talk with the saved model that you want to use when you are deploying this TensorFlow model serving. Now, it basically works very seamlessly, where you can get the model from TensorFlow Hub, and then we'll be able to deploy through TensorFlow model server in no time. And then I have another one. Let's see if we can complete this. I think this will take quite a bit of time. I think I didn't push this to the GitHub. I will do that by the end of today. This notebook actually shows the TensorFlow datasets, which is kind of nice, where if you want to kind of look at different types of TensorFlow functionality, generally we need a TensorFlow dataset. And on the TensorFlow datasets library, you can basically get all of these datasets very quickly and very easily. You can use this TFDS load to even create training, validation, and test datasets, which basically provides this out of the box. And then on top of that, the interesting piece in here is when you have the dataset there, I want to show the tensor. Well, let me actually start this. So the one thing I want to show in here is the TensorFlow load extension. I think there was a talk that talked about different types of extension in the notebook. With the TensorFlow 2, now we have an extension, TensorBoard. You can actually load this extension into the notebook, and then we'll be able to look at the logs within the notebook. And I will show what this actually looks like. The other pieces are very similar to what I've been showing so far. The model training will take quite a bit of time, but hopefully we will get there. And after you load that extension, the logs line, which is basically the path that you want to output your logs, you can use the same exact, I think this is called Jupyter Magic or something like this. You will be able to use this on the log there, and then you will be able to see there. Since you are executing this in the notebook setting, you need to find this on the terminal for the process ID on the TensorBoard to kill it. I don't think this is possible unless you are using the bash script in here. So I will just go to the terminal to see what it actually is doing. And then after that, maybe while that is completing, I will show a couple of other things. Now we have this plot model piece. where it can actually show all of the layers. This wasn't there before, I believe, on the TensorFlow 2. If you are using Keras API as well as the Keras module within the TensorFlow 2, now you can basically plot what does the architecture looks like out of the box. This is again very similar to scikit-learn. Scikit-learn also has a functionality to output random forest or anything that is like very structurally different than what you would normally use. TensorFlow also now supports this type of kind of output on the model itself. And then earlier, this was already there on the Keras. TensorFlow didn't support this, but Keras has this for a while. And then that was pretty much of it. The TensorFlow serving again is similar to what we went through. Let me show where I did get this. Yep. Okay, this is almost there. And then I will show the logs piece on the tensor board. I need to kill the previous one, I think. I don't think this is it, but let's see. Unfortunately, this doesn't seem to be working. Maybe I need to shut this down. I wish I did this demo, but this is fine. And then the last notebook I want to go through. I won't be running this. This will be taking a longer time. This is also the text piece of it that basically goes through the text classification piece. Again, we are downloading an IMDF DB dataset from the TensorFlow datasets. And then you can run this in Colab as well. And then you can basically build this on your own as well. This will be the text classification piece on top of it. And then I want to show one more, the SH file, and then I will be completing this. Perfect. Okay. If you want to write a client, I will show a simple client. This is one of the notebooks as well. The async doesn't really work in the notebooks, so I wanted to separate out as well. And if you want to use HTTP, this is pretty standard requests code. Now you are importing requests, and you want to, output basically the response content from whatever you are going to get from the TensorFlow model prediction server, and then basically get the output. On the async IO piece, you can basically write the function that is going to be the one that is going to be probable to be bottleneck. You can wrap this into an async function, And then based on this async function, you will be able to get the model output. Because more often than not, you may want to do something else. And especially for images, the serialization and deserialization, base64 encoding may actually take quite a bit of time. So there might be some value to make the communication to be asynchronous. I kind of wanted to showcase on how you can actually do this. Now with the Python 3, I think 3.4, we have now asynchronous function executions. So you can wrap the areas where you can wait for a long time into an async function and then execute this in an asynchronous manner rather than the eager execution that generally Python used to use to further optimize on some of the communications in here. If you are not happy in some of the other pieces where there is no necessarily TensorFlow involvement. In here, for example, we are waiting to download some piece of data from a URL. And this has nothing to do with the TensorFlow. It is completely based on the network. And you may want to do something else on top of that function. So there might be some value in some of the areas if you want to make it as an asynchronous process. This is pretty much all I have for today. Thanks. Yep.
In notebook 3, there's a main function that says send a few requests to warm up the model. What does that mean?
What is it?
Send a few requests to warm up the model.
Basically, in the initialization, so I mentioned warm-up data script as well. When the model comes along, TensorFlow team suggests that you need to warm up the model. Yeah, a couple of times. It doesn't matter what it actually is doing. This is what I'm actually doing this basically in here. This is basically the area that you are talking about. So now I'm trying to measure average latency. In the first 1 or 2 requests, there might be some behavior that may not be very consistent with the rest of the model prediction. And TensorFlow has actually a great blog post where there was this engineer. Let me explain this way. They observed a model prediction latency at 12 p.m. on the weekdays every day for a long time. Basically, and try to understand why it is 12 p.m. PST, why there is anything. And they are looking at, if there is any server deployment, if there is anything like this, and it is hurting their P99. There is not much customer impact, but they are getting alerted, they are getting paged, and they want to understand the issue. And they couldn't find out the issue for a long time. And then they realized there is this engineer that is around 12 p.m. that goes to the basically lunch break, where what he was doing is he was getting his lunch and then pressing a button to deploy the model. However, since there is no warm-up, when model is actually going there, even they are using version policy and whatnot, the first request or first few requests are actually showing higher latency than the rest. And that's hurting their, basically the P99s. And this is basically to try to accommodate that piece. And they are also suggesting a warm-up data script, which you can actually embed onto the server model configuration, onto the conf file. That actually basically does absolutely nothing. Just gets the data, passes to the model. It doesn't even look at the prediction itself, but just to make sure that there is at least a couple of requests that went to the model before it actually starts serving it.
You're just priming the Docker containers to get the model loaded.
That's exactly right.
All the time.
That's right, exactly right.
Does that need to be done right after the deployment, or does it need to be done after each reboot of servers?
So, yes. In the TensorFlow model serving, you can actually embed this. So you don't have to go through the Docker layer. However, if you already have Docker layer warm-up, you can also do that.
Well, you run into a bit of an issue, right? When you have a dynamic deployable, right? So you deploy this model and you have this initial containerization of 3 or 4 containers, right? But you have a max of 100.
Mm-hmm.
Every time a new one spins up, it has to get primed, right?
That is correct, right? For each Docker, right?
And are you saying you can like preload that? Where like, I know I'm gonna have to spin this up, so it spins it up before it uses it?
Yes. So if you look at this, basically in here, there is this, actually, I can just close this guy. Before it registers, and register means different things based on the infrastructure. Sorry, actually I highlighted the wrong line, I think. Yeah, this one. So before the model actually starts, you can actually say, because the registry and the exposing the HTTP REST API is happening in here. Before exposing these models in the startup, you can provide this in the warm-up requests, which is, I believe, basically a request per line. And then make sure that when model starts up, you provide those warm-up requests. And then after model will get warmed up through requests. And then the exposing that model in the Docker will kick off later. This will be basically the model-based warm-up. You can also do, after you do this, on the Docker file, before registry, right? Now we expose the API endpoints. Wherever it is registering these API endpoints in your infrastructure, you can also make a couple of requests to the endpoint that doesn't have the specific version number, so that whatever the new model is going to come up, it will be also warmed up through the Docker layer. The first one is basically supported on the data model file itself, and this is not directly related to Docker. This is basically how it will expose the HTTP and gRPC endpoints. However, if you are using Docker or Kubernetes, you can also do warm-up from the HTTP and gRPC from kind of outside of the Docker container. Does anyone have questions? Cool. Yeah.
There are so many things that are trying to solve the same thing. Do you have any quick overview or comparison between the different things?
Currently TensorFlow model serving is actually doing a good job. I am really happy about what we have right now. I think they are still trying to improve some of the flow on the training piece. I was showing this earlier on the training piece. Where was this? This was here. So in here, there I think still there will some work that needs to be there for sure. They are going to try using Kubeflow. I think today there was another talk. There was another initiative that they have TensorFlow extended, which makes it more component-based various pieces like pre-processing, data input, putting that data into the model, the training piece aspect of it. I think there is going to be much work that is going to be there. What I am more interested in what it happens in here. I think we still don't have a good solution in the industry where how do you make sure that the model is passing a number of smoke checks. Similar to what we have unit tests, we have regression tests in the code. As far as I know, there is no automatic or smart way for us to be able to deploy the models in a much safe way. Because all the time we are doing these offline evaluations, we are doing online evaluations, we need to perform A/B testing, we need to do a bunch of stuff just to get the model into production. I think there will be some work that needs to be done there for sure. Like I want basically a good CI/CD platform for machine learning. Not sure how that is going to be there, but I think there is definitely a need. And the other thing is currently Google is pushing for Swift, pushing for TensorFlow JS, probably for a number of different use cases. I wish there is this standard format which basically powers everything, like similar to this arrow. For example, it is columnar data format. It has a bunch of clients, and then everybody else is using. I think what they are going to do is with the state model, they are going to try this type of approach. I don't know if this will be the state of art. It will be great if this would be the case, so that instead of me, for example, I do Python in here, but maybe my API layer is Java, and I will still be able to use state model through Java or a JVM language, which currently, for example, TensorFlow 2 doesn't support on the state model, so you cannot use JNI, Java native interface, where in the TensorFlow 1, you will be able to use that Java native interface on the API deployment. So there needs to be some work there. It is not as streamlined as they are promising right now. However, I would think there will be some improvements for sure around those areas. I hope the state model will be the final model specification format that most people will decide, because there are also other initiatives like Facebook's, Microsoft's. There is this platform called ONNX, I think. This is yet another, exchange format. It has more support than Google. However, as far as I know, there might be some libraries that will convert before back and forth. But I wish there is like this standard format that and other libraries can kind of reuse and utilize. But we will see. Yeah, this also is basically trying to solve. That is correct, yes. If you have like an MXNet, which is from Amazon, or PyTorch from Facebook, they are specifying an exchange format. So basically, you have MXNet model, you have PyTorch model, you have TensorFlow model, and then this converter will take care of those conversions. But also, I think they are also trying to do maybe a standard format where rather than you converting one to another, you will convert to one to something, and then that something will be able to easily interpretable than the other libraries.
PMML or Pickle?
Yes, PMML is exactly the, like it has been there forever, or Pickle, yeah, exactly. Cool. Thank you.